Okay, in the folder for today, you'll find the notes that I handed out on Friday. That's the ones I'm going to work off of today. And I don't think I have any. So you just have to write those down. You'll also find a homework or a quiz, take-home quiz set for Friday, and then on Wednesday's folder there's a set for next Monday, and then the Chapter 121 problems for top hat are due next Wednesday. And I haven't gone through to see if we need to eliminate any of them because I didn't assign those. I'll do that this afternoon. On Wednesday we'll also have our quiz where I will give you a table of 10 rows where you're going to have to put the substituents. So you're basically going to have to reproduce this. You're going to have to put your substituents in, then tell me whether that group is electron donating or withdrawing by induction or resonance, and whether it's an ortho, para, or meta director. So you're going to need to know each one of these substituents. I will give you the H. There. This table from 1 to 10. So I'll give you the H at 5, and you're going to have to put the other ones in order, as you'll see why today. Okay. So for each one, again, you're going to need to know, is it activating or deactivating by resonance or induction, ortho, para director, or meta director. Okay. And we have to know that for next Friday. So once you got it in there for Wednesday, keep it there for the rest of the semester. Okay, so here's where we were at on Friday. We were going to take something like methane or toluene and react it with HNO3, H2SO4 to add a nitro group to the ring. So the first thing we need to do is look at our reagent and know what electrophile we generate. Okay. So while you'll know, hopefully on Wednesday you'll have all of the groups in order of activating, deactivating, etc. That's only half the battle. The other battle is you need to know what reagents form what electrophiles. So in this case we form a nitro group, and where does that go relative to the methyl group? So if I'm going to write the product or products of this reaction, where am I going to put the nitro group? Meta? Ortho, para? So what is it? So this is the director. The nitro group is the electrophile. So the group that's already on the ring makes the direction. And so it's going to direct ortho and para to itself. So an NO2 ortho and an NO2 para. Now you could say, could I put the NO2 group over here? Yes, that would give you the same product as the first one. So what you don't want to do is you don't want to write the same product twice. Used to be I would take points off for that. I won't give you any extra points for writing the same product twice. So you want to make sure that this is the same as having the nitro group here. Okay. So that requires that I know my groups. But now what we're going to do is now we're going to take each one of those and I'm going to react it with another equivalent of H2SO4 and nitric acid. So, how do you do that? Well, the group that's well, here's how the book does it. And I used to do this for the first probably 12, 13 years. Well, no, it was more like 10 years that I taught. So what they talk about is, well, look at the groups that are on the ring. If there's two activating groups, then the one that's most activating is going to do the direction. Or we talk about, do they point to the same positions? Or we say, well, if it's an activating and a deactivating group, the activating group's going to win. Or if they both point to the same direction, fine. If they don't, then the higher, then the activating versus the deactivating group wins. And I used to go through all of those scenarios, and then maybe around 2000 or so, somebody in class, and I know who this person is. They're a physician down at Akron Children's Hospital, and they raised their hand. They said, "Do we really need to do all of that stuff?" And I kind of looked like, "Well, I just said so. What do you mean?" And then they said, "Well, couldn't we just use the group that's highest on the chart and just use that as the director?" And that's genius, because I hadn't thought of it to that point. So that's what we do. So if we're looking at, all right, where's my arrow? So if we're looking at that chart that we had on here, where's the chart? So if we look at this chart, now this was the chart that we had the other day, showing the activating and the deactivating groups split up on either side. So if I take this and I bring it from top to bottom, I get this. So the question is, which of these groups is highest on the list? And I guess I've given these numbers from 1 to 10, so it's the group with the lowest number, but it's the group that's highest in this group from 1 to 10. So not highest in number, but highest in activating. Okay. Because this morning I asked the question, so then I asked the question, I said, okay, so methyl or nitro, which one is the highest on the chart? And they said nitro. And I'm like, okay, our numbers are confused here. What I'm looking at is I'm looking at the one that's at the top of the chart, or higher up on the chart, or more activating, or less deactivating, whatever you want to call it. And that group is the methyl group. So the methyl group is going to do the direction in each one of these cases. And so you can skip past, well, do they both point in the same direction, blah, blah, blah. Just let the group that's the highest on the chart do the direction. And then that skims it, or that trims it down considerably. So in this case, my methyl group is going to direct ortho and para, and if there's already a group in an ortho and para position, or there's already a group at that position, we can't add another one. So in this case, my methyl group is going to be here. My first nitro group is there that I added, so I'm going to get an ortho. Then I added para, added first nitro group para, or second nitro group para, and here it's ortho. So these are my two products for the reaction of the ortho nitrotoluene. Over here, on this one, where am I going to add the nitro group? To A or to B? I heard 1A. We agree with A? So in this case, the methyl group beats the nitro, and so it's going to... Now, whether I put it on the left ortho position or whether I put it on the right ortho position, it doesn't matter. They're the same product. And if you're thinking about adding it to both of them, no, because we're just adding one nitro group. So I can go on either the left or the right ortho position. And so we continue on. So what happens with all three of these molecules is if I took all three of these molecules and I reacted it with another HNO3 H2SO4 molecule, I would add another nitro group, and all three of those products would then produce the 2,4,6 trinitrotoluene, which, as I said on Friday, that's trinitrotoluene. And so because I've embedded 3 gas molecules into this, it's a very good explosive, and it's TNT, it's dynamite. Right. Now, a dynamite stick would not just have TNT. The critical part is putting the TNT in, usually with clay or something like that, to make the dynamite stick only explode when you want it to explode. But this whole process gets a little touchy, because once I put a nitro group on the ring becomes less activated. And so to put the next nitro group on, I'm going to have to heat it. And there's a fine line between heating it and putting the nitro group on the line and heating it and blowing it up. And this is what the Nobel company, what Alfred Nobel's company did, was that they basically made dynamite and blasting caps and a whole bunch of other things. And then at the end of his life, because many family members got blown up during this process, he gave all his money to the Nobel Foundation for peace prizes and Nobel things, Nobel prizes in chemistry and medicine and economics and all of that. The Nobel company still exists. It's Nobel something. There's one in Cleveland. So that's how you can add groups, but as the group becomes more deactivated, you have to apply a little bit of heat. Right. And I know a little bit about that because, as I said on Friday, Alfred Nobel is like the 6th cousin X times removed, and I think it's like more than 10 from one of my great-grandfathers. Right. But I only have 16% heritage according to the DNA spit test. It kind of blows my what my self image was, because I always thought of myself as Swedish, and that's only 16%. There's more of other things that I don't have any idea about. But that's a topic for another class, in terms of looking at your DNA heritage versus what what you grew up with as a kid. So anyway, so that's how we do this. We have to know our chart. Okay. So let's go and do this reaction. So let's say I've got a CO2 with an NH2, and I'm going to react that with Br2 and FeBr3. Okay, so since I don't have my iPad with the wheel of everybody's name, we'll do it by numbers, going 1 throughout. So number 12, 1, 2, 3, 7, 8, 9, 10, 11, 12. Sarah. First question, what electrophile are we forming with Br2 and FeBr3?
Is it going to be Br?
Br plus. Okay, so we're forming a Br plus. Next question is, which of these two groups, COOH or NH2, is going to be the director? So let's see, number 19, 12, 13, 14, 15, 16, 17, 18, 19, Anthony. Anthony, which one's going to be the director in this case, COOH or NH2? COOH? The one that's going to be the director is the one that's higher up, has the lower number on our list of groups from 1 to 10. COOH is not number 1, right? NH2 is number 1. So NH2 is going to be our director. What kind of group is NH2? Activating, which makes it ortho-para. So it's going to direct ortho and para to itself, which means that's A, positions A and C. And so I'm going to get 2 products in this reaction. I'm going to get, and notice that, you know, when you're writing these products, particularly next week when you're under excruciating pressure to do so, the first thing we start with is just by writing the structure of the reactant. Now we can just put the group in. Of course, you got to know what group and where to put it, so it's not like you can just guess at this. But where am I going to put the Br? I'm going to put it ortho to the nitro, and I'm going to put it para to the nitro, bless you, and since both of those are different products, then they are different products. Okay. If they were the same product, we only need to write it once. The other ortho position is taken up by this group, and so that bromine can't go there. Right, so that's how we do these problems. All right, next is our table, and then our number 1 to number 10 table. Okay, here's another one. All right, what am I adding here? Okay, I'm adding an NO2 plus. There's only 2 positions that I can add to, A or B. So, number 6. 1, 2, 3, 4, 5, 6. So, Amelia, where should the NO2 go? Onto A or B? Do we agree? Nobody's agreeing. One person's agreeing. 2. Chlorine versus OCH3, which one is the most activating? OCH3, because it's number 2. So that means that it's going to direct ortho, its activating group. So it's going to direct ortho and para. There's no para position. So that means it's going to direct to B. So in this case, the product will be adding the nitro group there to the ortho position to the OCH3. Right, so a couple things that we're going to have to learn. We have to learn the table for Wednesday, obviously, but then we need to know about our electrophiles and how we generate them. There's one more, and I'm going to apply an additional rule here. So here we have ortho-bromo-nitrobenzene. And the first question we have to ask is what's going to be our electrophile. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Claudia. So again, an alkyl halide plus AlCl3. Call out for help if you need it. You need help? Okay, let's you need help from number 7. Josh, you're number 7.
So we're going to create
So whenever we react an alkyl halide with aluminum trichloride, the aluminum trichloride is going to take the chlorine away and we're going to end up with an alkyl carbocation. Remember last week we said it really wasn't a CH3+, but it's going to end up adding a CH3 group to the ring. Okay, so that's our first step, is what are we adding? Who's the director in this case, because they're both deactivating groups? Which group is higher up on the list? Which one? BR is higher on the list, so it's going to do the direction. What kind of director is BR? What did I hear? Do we agree? Yeah, it's a halogen. So halogens are deactivating groups, but they're the exceptions to the rule. And so they're the exceptions being that they they direct ortho and para. So in this case, it's a deactivating group, but it is the exception. So it's going to direct ortho and it's going to direct para to itself. So there is possibility of 3 products here, because the bromine will direct ortho and para to itself. Here's the problem. The problem is when we have two groups that are ortho or that are meta to each other, we never add in between those groups. So we don't add in between meta groups. And the reason for that is because it's a steric hindrance issue. There's not a lot of room between meta groups. And somebody asked me this morning, well, what if you had a small group? Could you add a small group there? And I'm like, well, okay, give me a small group that could add in there. And they said H+. Small group, but we never add an H+ to the benzene ring. So everything else is going to be bigger than an H+. So I just will not add to add in between a 1,3 set of groups or add in between meta substituents. And so instead we're just going to get a CH3 added to the para position, and we're going to get a CH3 added to the ortho position. And when you have to write these products out, if you get two distinctly different products, then you do have to write them out. So if it's a meta direction, there's just one. If it's an orthopara, you have to write both. Or if it's meta directing and it gives two different products, you have to write those two different products as well. Okay. So these are the kinds of problems that I put in the first take-home quiz set. We're writing the products of these kinds of reactions, and I didn't get a chance to photocopy them. They're in today's folder, and so you want to print those out, but they're due on Friday. And there's a number of these, which is why I gave you a couple days to do them. So this is how we handle adding electrophiles to the ring. You need to know what the electrophile is, and then if there's more than one substituent, whichever one is the highest on the list is the one that's going to do the direction. So we need to know our electrophiles, and we need to know the reagents that give them to us, as well as the listing, the rankings. But these problems are more interesting. These are more fun problems. When I give you a benzene ring and say, how do you make this from benzene? So how would I make meta-nitroethylbenzene or meta-ethyl nitrobenzene, whichever one you want to call it? Now, the first thing I need to know is I need to know how do I add an NO. What reagents do I use to add an NO2 to the ring? HNO3 and H2SO4. It's been on the last 6 or 7 pages. How do I add an ethyl group to the ring? Number 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we're back to Sarah.
Would you do and then
How's that look? So this is the Friedel-Crafts alkylation reaction. And so that's how we would add our CH2CH3 group. Okay. So what's going to get more difficult is you not only need to know what electrophile the reagents give you, but you need to know what reagents to use to get a particular group on the ring. So you got to know them backwards and forwards. So I need to add nitric acid, sulfuric, and ethyl chloride and aluminum trichloride. Now, I'm going to add those. This is a 2-step process. Does it matter the order in which I add these reagents? If it didn't, I wouldn't have brought it up. So which group has to come first? Or doesn't it matter? What? The group that directs. What do you mean by that? So the group that I add onto the ring first has to direct meta. Okay, which group is that? NO2. So what do I need to add first? NO2. So I need to add HNO3 first with H2SO4. Add that first and then followed by ethyl chloride and aluminum trichloride. So order does matter. If I added the ethyl group first, I would not get that product. I would get ortho and para, which is not what I asked you to make. Okay, so that's another issue that we've got to deal with. So you have to begin to think about the substitution patterns and which group would I add first. So in order to answer this problem, I needed to know those three things: how to add the two groups, and then which group to add first. So we don't know necessarily a lot of reactions to add groups to the ring. You may think it's a lot of reactions, but it's really not. So let's pile on a few more. Let's add a few more. So here's an interesting problem. So tell me, I've got two groups to add, a carboxylic acid and an SO3H. Give me the reagents to add whichever group you would like. Zach? H2SO4 and SO3 will add the SO3H group. Agreed with everybody? We agree with that? Okay, how do you add the carboxylic acid group? No. No, don't ever start your answer with "I'm not sure." Good, somebody fell for my trap. It's not a trap, but we might as well deal with this reagent. So, let's see, I have to be careful how I say this. This is a half, and I have to put the word carboxylic acid in here, because this morning I just started with half and forgot the carboxylic and stopped. So this is a half carboxylic acid, half acid chloride. On paper it looks good until I do this. No. The problem with this molecule is it's really difficult to make. First of all, I would have to make this by using carbonic acid and adding SOCl2 to it, and only get one chloride to add. So we're going to find this reagent isn't allowed to be used because it's not stable. So you might as well have brought it up so that I can do this, whatever, that. No, you're not. That's the reagent you're not allowed to use. And statistically, 3 or 4 of you will still use this next week on the exam. That's just how it works. So no, that reagent, it looks good, but it's not going to work. So we have to go back, and we have to come up with a multiple step method. So you want to put a methyl group on the ring first, and then you want to use KMNO4 to react to make the carboxylic acid. Yes, that's one method of doing it. So it's a 2-step method, The two-step method is put a methyl group or put any group on the ring. So we would use RCl, AlCl3. Put any alkyl group on the ring. So this doesn't have to be methyl, it could be R. And then oxidize it with KMNO4. And that's one way to put a carboxylic acid group on the ring. And I'll also point out at this point that this method, the first group I added was an orthopara director, and I ended up with a meta director on the ring. So if you ended up with a product that you were trying to make where the two groups were ortho to each other, but they both ended up being meta directors, this is an example where you put on an activating orthopara director first. So I might put this group on the ring, put the second group on the ring, and then convert it to a carboxylic acid. So that way you would get them in a kind of an unnatural position where you have meta directors, but they're ortho or para to each other because the group I put on first was an orthopara director. So that's one. Good. The next one we have to think back a little bit further in our memories. Fortunately, you have me here to jog that memory. So here's a three-step scheme to get a carboxylic acid group on the ring. How do I put the bromine on the ring? BR2AlBr3 or FeBr3. What do I add to the alkyl bromide or aryl bromide to make a Grignard? Mg no 2 plus. Mg 2 plus is the ion. I just want Mg. And then what do I add to the Grignard to add a carboxylic acid? CO2. Then H plus H2O. So the CO2 with the Grignard makes carboxylic acid. So there's no real easy way to get a carboxylic acid group on the ring other than to do these 2 and 3 step syntheses. So if I did this, it wouldn't matter what group I put on the ring first because they're meta and these are both meta directors. So that's how we get a CO2 group on the ring. Now, the other groups that are on the ring, what I really need to do is I have a bunch of groups in my chart from 1 to 10, and I don't know how to put them on the ring. Starting with group number 1, an N group. So how do you put an NH2 or an NHR or an NR2 group on the ring? Well, those would come from an NH2 group. How do you put an NH2 group on the ring? You can't in one step. Instead, what you do is you reduce a nitro group using iron or tin with HCl and heat. So this reduces my NO2 group to an NH2 group. So tin, iron, HCl, and heat reduces a nitro group to what's called an aniline. And I know how to put the nitro group on the ring. I mean, we've only done that 7 times today. What?
The lithium tetrahydride?
No. No. Those only work with carbonyls. So lithium and sodium borohydride reagents only work with carbonyls. This is pretty harsh. This is a metal with HCl and heat. The only reason I'm getting away with the HCl is because it won't react with the benzene ring.
Are we also allowed to use H2PEC?
No. Okay. Sure. What was that? Palladium and... So it's palladium absorbed on carbon. So, yeah, I suppose that would work. So, PDC means, first of all, palladium is super expensive. Platinum's super expensive. And so, you just need it on the surface of something that's cheap. So what they do is they absorb palladium or platinum metal onto the surface of carbon. Because then you don't need a chunk of solid palladium when you only need the surface. You just need the surface on something cheap like carbon. So that's what the PDC means. We'll talk about that more on Wednesday and Friday. And then hydrogen gas, you're just doing your thing. Either one. But I'm going to give you both. So you need to know both of them. So that would be a reduction of an NO2 to an NH2. So now we can add group number 1 from our chart. And that's about it. Because sadly, I need to put an O on the ring. How do I do that? How do I put a C triple bond N group on the ring? We've already done this with preparing a carboxylic acid. And I'm going to come back to this later. So, a collection of reactions that allows us to put an oxygen or a C triple bond N group on the ring is done through what's called a diazonium salt. So, once you put your NO2 and reduce it down to an NH2 on the ring, we're then going to turn it into what's called a diazonium salt. And the way we do that is we react the NH2 with HCl and sodium nitrite. Okay, that's not nitrate, that's NO2, is nitrite. So reacting HCl and sodium nitrite converts the NH2 into what's called a diazonium salt. The diazonium salt usually has a chloride as its counterion. Now, when you're making a diazonium salt out of just an alkyl group, we normally don't do that. This is going to be a great leaving group. Of course, it's a nitrogen group. It's nitrogen molecule embedded in an organic molecule, so it's also going to have a tendency to explode if we're not careful. But if I can put that N triple bond in conjugation with the ring, it's more stable and it's safe. For the most part. So we could make this in the lab. We could take aniline and we could make the diazonium salt out of it. Now if we do that, and we have to go through these first 3 steps to get to the diazonium salt, then we can do all sorts of reactions to replace that NN triple bond with different groups. And the first set of reactions are what are called the Sandmeyer reactions. So if you react a copper salt with N triple bond N, what you end up doing is replacing that with whatever the X group was. So you could do a Sandmeyer reaction and use copper chloride, copper bromide, or copper cyanide. And so the important thing here is I know how to put chlorine and bromine on the ring, but what I don't know how to do is to put a C triple bond N group on the ring. And so the Sandmeyer reaction is the way to do that. So you make the diazonium salt, and then you react it with copper cyanide. Okay. So that's one method, and now we've got group number 8 on the ring. But these But we can also do lots of other things with diazonium salts. If you take the diazonium salt and you treat it with acid and water, you get the phenol. So that's how we can add the OH group to the ring. If you use HBF4, you can put a fluorine on the ring. We didn't really talk about adding fluorines to the ring. We just talked about chlorine and bromine. So now I can put a fluorine on a ring. Do I want to put a fluorine on the ring? There's a number of pharmaceutical drugs that have a benzene ring with a fluorine in it. And so if I want to make any of those molecules, I'm going to need to put a fluorine on a benzene ring. And that may not happen naturally. So use HBF4. Use potassium or sodium iodide with the diazonium salt, and you'll add the iodine to the ring. So now I can add any of my halogens. And if you want to replace the diazonium salt with an H, you use H3PO2, which is a really bizarre hydrogen phosphate. But that will put the hydrogen on the ring. Why would you want to do that? There's probably a reason, but it's pretty obscure. Yeah, if you wanted to remove a nitro group, or if you wanted to block with a nitro group, and I'm going to talk about blocking here in a moment, or 72 hours, whichever comes first. So these these aren't Sandmeyer reactions, but these diazonium reactions now give us the opportunity to add all sorts of things. So I said before, we just had a few reactions that'll put electrophiles on the ring. We now have added, 10 more reactions to that in a matter of a few minutes. So there's 10 3x5 cards gone like that. And enough brain cells and neurons to put those 3x5 cards in. Preferably permanently, but at least for the rest of the semester. Okay, so now I can add lots of stuff. And I'll just end it here with the reason that this diazonium salt actually became kind of important was that if you prepare the aniline and you add and make the diazonium salt, there's two resonance structures for the diazonium salt. One where the N plus is on the inside and one where the N plus is on the outside. When this N plus is on the outside, this is just a really big E plus. And if you have an activated group on the ring, then what will happen is that activated group will add this E plus primarily to the para position, simply because it's too sterically hindered to add it ortho. And you end up making this compound, which is the structure of what do we call a diazo dye. Now, the whole dyeing industry, meaning adding color to fabrics industry, is a fairly big business. But it's been around forever. I mean, colorful clothing was always the sign that you were super rich. And so the idea that you could have dyes, first you could get dyes from creatures or plants, and the most famous of which was the royal purple that came from some creature that was on some obscure island in the Mediterranean that they would go dig up and then crush to make royal purple. And that's why it was royal purple, because only the royal people could afford it. And then Henry Perkin, who is an English wonder genius, like at 15 years old, had a chemistry lab in his basement, and he was trying to make quinine, which was a cure for malaria. And he used a bunch of these aromatic compounds, and what he probably made was a diazonium salt that was pitch black, but then when he started diluting it, it turned purple. And so he made one of the first dyes that it just so coincided that apparently they had Fashion Week in Paris back in the 1800s, and so royal purple was the color, and now everybody could have royal purple. Well, not everybody, but he could make a synthetic dye that he could now dye clothes with. The last thing, you've used these dyes, because if you've ever done a titration in general chemistry lab with methyl red, that's a diazo dye. So that's actually something that we just kind of gloss over, but making diazo dyes is a huge, huge industry. And we'll talk more about this on Wednesday. So on Wednesday we'll have our quiz, and then also on Friday then the notes or the questions in today's folder will be due.